Good morning, everyone. Glad you could join us today. I'm excited to be here with you guys. We're going to, excuse me, um, go over some logistics first and allow a few people to join us, additional people to join us. Again, my name is Chuck Cox, and if we haven't met before, I'm glad to meet you. Glad you could spend this hour with us. If you're interested, we've got handouts that I've included in the GoToWebinar panel. I've got handouts for this presentation, the previous presentation. I've also got a couple of other items there you may be interested in. If you have questions during the presentation or at the end, there's a section to ask questions. We will have a couple of polls. I want to go ahead and put a plug in for our survey. Since this is the fourth installment in this series, I need your assistance in kind of getting a feel for what additional or more advanced topics you would like to see a presentation on, specifically around P25, but then also if you've got ideas for other topics that you might be interested in. Again, we've got a number of people joining. If you have not had a chance to join us for the previous presentations, then I will be putting up a landing page. You will get an email next week with a list of the entire series and links, and it will also be linked off of the video library on our website, and you'll have that link at the end of the webinar, which you'll be able to share with others if you'd like. I will also try to make sure that all of the handouts are available on that landing page. Okay, all right, we're a couple minutes in. Looks like we've got a good group. As I always do, I would like to thank you for joining us, and I want to remind you that I consider you guys my heroes. You guys are often unsung heroes. You make sure that the communication lines are open when they're needed. You guys don't always get the spotlight of attention unless things go wrong. And so I want to acknowledge the important work that you do that doesn't always get seen by the public. And you are truly my heroes. And it is a great privilege and honor for me to be with you today. We're going to spend this time learning. I will present information. Hopefully you will find something new, and I also want to learn from you. So I want to encourage you to be thinking of, if you have a thought or you want to have a follow-up conversation, make notes or pose a question in the question section or connect with me directly. I would love to continue this dialogue. My name is Chuck Cox, and I'm product marketing engineer at Astronics Test Systems. I've been involved with the Freedom Service Monitor test equipment line since before the R8000, when we were still doing the R2600 series, and have been involved as a development engineer, manufacturing engineer, field sales application guy, going to talk to customers before, after the sale, doing training. I find myself now more in a marketing and product role. And again, thank you for joining me today, and we'll go ahead and get our presentation started. We will start out with a poll. Tiffany, our lovely assistant Tiffany, is an amazing lady, and she is going to open up our first poll. And I'm going to open up the correct window. Let me know what type of role you are in. This allows me to make sure that my message is tailored to the people on the webinar. Excellent. Usually it's a majority of radio technicians, but there are often others such as engineers or supervisors or managers. And I want to say a special hello to all of our partners, all of our manufacturers, reps, and distributors that are on the webinar today. You guys are awesome. You guys do a great job. You have great technical expertise and you're always eager to learn. Okay, looks like we've got about 60% radio techs and about 20% engineers. It's always difficult to tailor the presentation to a broad audience. I'm going to try to present enough depth that there's something there for everyone. I might cover some areas a little more quickly, rapidly, brush over them. Again, I'm trying to make sure there's something there for everyone. And we try to stick to our allotted time. Okay, so let me go to my presentation and let's get rolling. So what are we talking about today? We're talking about P25 Phase 2 infrastructure. Our previous installment was Phase 2 radio test. So we're going to go over some of the same basics at first. So if you were on that previous one, you'll recognize some of the slides. I've done some clarification and added some additional content to that portion. But it's basically going over again, what is P25? What is P25 Phase 2? What do we need to do to test Phase 2 infrastructure? And how do we set up our test equipment? We're going to look at a customer scenario. We're going to, again, look at some of the standards and protocols. We'll go through some of the test methodology, and we will then do a live demonstration. In this case, this customer scenario is James, who's a radio tech at a it's actually a Texas radio shop. We're a county, and he's responsible for a large number of Phase 2 sites. And he uses his Freedom Service Monitor to quickly be able to test not only the base station, but also the duplexers, pre-selectors, filters, cabling, antennas. He's able to do that all with one piece of test equipment and instead of having to carry multiple pieces of test equipment. And this quote here is typical of what we hear from most of our customers. The equipment's easy to learn, easy to use, helps me get my job done, and doesn't get in my way. So that is a typical customer experience. Again, just real briefly, APCO P25 standards come from the TIA 102 specifically. P25 was user-driven, jointly developed by APCO. It's an open architecture, meaning that you could have P25 systems developed by different manufacturers, and they should be able to interoperate as long as everybody's sticking to the standard and not using custom features. And key benefits, interoperability, obviously, the fact that it is an open standard, and backwards compatibility. Again, we've seen this before if you've joined us before, but I wanted to highlight P25 Phase 1 versus Phase 2 differences. Phase 1 is strictly FDMA. We'll talk about that in a little more detail, what that is. Phase 2 uses FDMA for the control channel and TDMA, 2-slot TDMA for the voice or data channels. Modulation types, Phase 1 uses C4FM, and if you're on a simulcast system, the outbound could be LSM or WCQ-PSK, excuse me. In Phase 2, we have two different modulation schemes, one for inbound, one for outbound. So the HCPM and HDQ-PSK, and we're going to cover that here in a little more detail. Oh, let me go back one slide. The fact that there are two different modulation schemes, one inbound and one outbound, means that there's no way to do conventional P25 Phase 2. You can't, the radios and the system can drop back to Phase 1, and the radios can talk directly to one another in Phase 1. But Phase 2 is strictly a trunking system, since the the radios transmit using a modulation scheme that the other radios cannot receive, and vice versa. Okay. Very quickly, I mean, 99% of you guys understand this, but it's always good to see a good picture of this. FDMA, we've got a 12.5 kilohertz slot and we're transmitting continuously. If we want to put 2 conversations in there, with the narrow banding mandate, we're trying to squeeze more channels into less bandwidth. You would have to put 2 6.25 kilohertz channels inside that 12 kilohertz. So the other way you can expand your capacity is TDMA, time division multiple access. What that means is when the radio is transmitting, it's transmitting at 12.5 kilohertz, but it's transmitting alternately 2 different conversations can be going on at the same time, and we'll see in the next slide how that works. So here's a little diagram I put together. You can see that the base station here is in the middle, and there are 2 simultaneous conversations going on the first slot and one on the second slot. They're often called slot 0 and slot 1, so you'll see that terminology, and it could be a little confusing, first and second, or 0 and 1. The outbound from the base station is the HDQ-PSK, and we'll get into details. Inbound is HCPM. And again, that's why this radio can't talk directly to that radio in phase 2. It's like speaking English and Spanish and not understanding each other. But again, it's 12.5 kilohertz, 2-slot TDMA. So you're slicing up the time into 30 millisecond time slots. Tetra protocol uses 4 slots. The TDMA phase 2 TDMA is 2 slots, 30 milliseconds at a time. Okay, and on to the next slide. Okay, the 2 different types of modulations. First of all, why are there 2 different ones, and what's some of the reasoning behind it, and what are some of the implications? So HDQ-PSK is harmonized differential quadrature phase shift keying. That's a mouthful. That's what's used outbound. That's what is transmitted by the base station. You can see from this eye diagram that the dwell time, this is time on the horizontal axis, and vertical is deviation. So you can see that the signal spends a lot of time near the deviation level that you want to achieve at this time. If you're in a simulcast system, or you're in a urban environment where signals are bouncing off of multiple objects, buildings and such, you're going to have multiples of these signals, and they're going to be slightly time shifted. So you can see the fact that these dwell, if you stacked multiples on top of each other and then were slightly offset, you'd have a much better chance of still being able to pick up a good signal. What this means, though, in order to gain this benefit, is that the modulation scheme is not constant power, and therefore you have to use linear amplifiers. So that's why it's used on the outbound side, where you have your base station transmitter with a more expensive, beefier linear amplifier. HCPM, the harmonized continuous phase modulation, is what is sent out by the subscriber radio. The continuous phase modulation means that it's able to keep the power level constant. And the reason that's important is that these radios that we've been using that need to be phase 2 compatible have nonlinear amplifiers, which is cheaper and simpler. And so in order to be able to do that, you've got to have a modulation scheme which can be properly that works properly with nonlinear amplifiers. It does mean, though, that on the receiving side, the demodulation of this signal is more complex, and so the processing power needed at the base station receiver, you only need to be able to do that at the sites. If the radios needed to be able to receive this, then you'd have to have a lot more processing power in the radios. That's the basic reason why we have 2 different modulation schemes. Again, just in summary, P25 modes of operation: conventional and trunking. Conventional is where you're talking one radio to another. You could be talking directly from one subscriber to another, or you could be talking through a repeater, which is just extending the range. It could be there could be a receive transmit frequency pair, but it is a one-to-one. You press, it activates, you hear it out the other side. You have to wait for an open channel to be able to transmit. In a trunked system, these are typically multi-site, multi-channel, and so there's a bank of channels. And when you key up, well, first of all, you have to talk with a controller and tell the controller, I want to key up, and it will assign you a channel. You switch over to that channel. So multiple conversations can be going on separate channels. In phase one, as we said earlier, the control and voice channels are FDMA. In phase two, the control channel is FDMA, but the voice or data channels are 2-slot TDMA. And a quick note that in phase two systems, if you have a radio that's part of a talk group that joins the talk group, and it's phase one only, then that voice channel, the controller will drop back to an FDMA phase one. That obviously takes up an entire 12.5 kilohertz channel, so you can't have as many conversations, but you still have the ability to talk to people who are on phase one radios. Okay, again, now since this was part of the previous presentation, if you want a little bit more detail, feel free to go back to that presentation, but I wanted to put this up again. HDQ PSK, this is what the base station is putting out, sends out 2-bit symbols just like the C4FM of phase one. And here are the different deviation levels. Again, it's harmonized differential quadrature shift keying. So you're sending a 1-1 or a 1-0, a 0-0, or 0-1. Those equate directly to those 4 levels, and that's what we were seeing on the eye diagram. This is your center frequency, and this is deviation above and below that center frequency. Things are a little bit more complicated on the HCPM side. Rather than encoding 2-bit symbols, we're actually encoding the transitions from 2 bits to 2 other bits. And so there's a distribution that you see here. And so just as a quick example, if I just sent a 1-1 and I want to send another 1-1, then I deviate 3 kilohertz below. And if I wanted to go from, let's say I wanted to go from a 1-1 to a 0-0, I would deviate 1 kilohertz below. And you can see there are more transitions that are encoded. So there's the fact that there's multiple transitions that can be encoded. You can't directly say, oh, this is 1 kilohertz below, therefore it's these bits. That's where you have to look at what the previous bits, the previous 2 symbols were, in order to figure out which ones of these transitions actually apply. That's hence the more complex demodulation. So what you'll see if you look at the distribution plot, again, center frequency in the middle, deviation up and down. This is the HDQ PSK, looks a whole lot more like C4FM. And typically, I mean, obviously it's going to depend on what's being transmitted, but the top, there's approximately the same number of symbols in each of those 4 peaks, whereas HCPM, because there are more transitions encoded at center frequency than this distribution, you'll see this pattern here, and you'll learn to recognize that when you're using the test equipment. Moving right along. Okay, let's talk about frames, super frames. Again, this was in the previous video. Just wanted to touch on it real quickly. We've got 2 different slots. So here what you're looking at is what we call the power profile. This is time across the bottom. You can see 30 milliseconds is the middle, 60 milliseconds. And this is power level on the vertical scale. So this particular radio is transmitting on the second slot, or slot 1. And you can see that it's not transmitting, then all of a sudden it's ramping up, and it's got to be at full power before this. This is the standard, and it's got to stay full power until this point, and then it drops back down. So 2 radios are talking and listening alternately. Now that's called 1 frame. That's 2 slots, 1 frame. But there is a super frame made up of 6 frames. The 6th frame actually inverts the slots. So all of a sudden, slot 5, if you're transmitting in the, like this radio here that's transmitting in the second slot, would be transmitting in the first slot in frame 6 of the super frame. And the reason behind this is that this allows the radio to be listening for 2 slots. You can see here there's 2 zeros side by side and 2 ones side by side. The radio can be listening for longer. This allows the base station and the system controller and the dispatch to have a path for signaling back to the radio. For example, if someone is sitting on their mic, in most systems, there's no way to prevent that from happening. The best you can do is basically tell the system to ignore that. It can still cause interference. Whereas with Phase 2, you do have the ability to send a signal back to the radio that says, shut yourself off, in terms of cut your power, go to receive only. So anyways, this is what makes it possible, is the fact that you've got this 6 slot that's used for signaling in both directions. Moving along. Okay, so let's talk a little bit about, last time we talked about subscribers, Phase 22 subscribers. So now we're talking about infrastructure. So what do we mean when we say infrastructure? These next few slides I borrowed out of a presentation we did for the R8200. That's the product that you see on the screen. It's just part of our R8000 series. It includes a single port VNA. But what are we talking about? And what is the advantage of having the ability to do all of the necessary testing in one unit? We have our base station inside the building or the cabinet, which includes our transmitter and a receiver. We've got a duplexer and other filtering. For example, we might have some receiver pre-selectors, so on and so forth. We might have other devices in the line, lightning arresters, so on and so forth. And we've got cable and connectors, adapters going up a tower up to an antenna. So let's break that down. So obviously the first thing is we want to be able to test the base station. It's basically a radio. It's a transceiver. It transmits and receives. It's basically, in terms of RF, it's pretty much the same thing as a subscriber radio, only it can put out more power and has to be able to, in this case, understand a different modulation scheme. But all of the typical things you would do in terms of frequency error, your power levels, your deviations, your sensitivity of your receiver, and then things specific to the RF environment at the site noise, desense. So that is your typical service monitor to be able to test the radio. The other piece of this is needing to tune duplexers, filters, pre-selectors, so on and so forth, RF circulators inside of transmitter combiners, things like that. And of course, the modern day service monitor also provides tracking generator functionality. And allows you to tune your duplexers with a great deal of accuracy and take a lot of the black magic out of tuning a duplexer. And things you're looking for there is you're looking for your insertion loss and you're looking for the level of isolation between the two paths. Moving on finally to the last portion of that, and that would be testing our cabling infrastructure and antennas. And again, there's different ways to do this. Typically, the kinds of things you're doing is you are looking for faults. So you might be doing a distance default, and your modern digital service monitors allow you to do frequency domain reflectometry to find out where the mismatches in impedance are. Whether in this case, whether you've got a blown lightning protector or you've got water ingress inside of a cable or at an adapter, whether you've got a bad jumper, and also to be able to sweep antennas to see if they're tuned properly. You can do this with your typical service monitor with the addition of an RF loss bridge. This allows you to look at reflected power and do distance default measurements. This works and it works great, but it can be a little slow. One of the advantages of this next generation of service monitor, the R8200, has got a built-in high-speed VNA, vector network analyzer, single port, and this allows you to have extremely high performance and be able to jiggle cables and see, the phase shifting happening. So you're not only able to pick out faults, but actually able to diagnose live problems with intermittent connections and things of that nature. For this presentation, we're going to focus on the base station. I've got a video on tuning duplexers. It's out there on our website. We did a great video with a live demonstration on the R8200 showing the sweeping of cables and antennas. I encourage you to view that one if you're interested. I've pulled some of the slides from that presentation into this one. But again, we're going to focus primarily on testing the transmit receive base station. Okay, again, this is the R8200. It's just the latest in the family of R8000 series service monitors. You'll recognize it by its blue color. We've got the R8100, which is the black, and then we've got the R8000, which is more of a gray or blue-gray unit. Okay, let's move right along. Let me check my time real quick. There we go. All right. And again, I want to be able to get to the demonstration. So again, these slides here, the same content from last time. I just want to cover them very quickly. Frequency error, again, we're dealing with TDMA. So if you're used to being able to use just a good old analog service monitor, you're going to have trouble here. TDMA, the radios are only transmitting half the time. And so getting some of these measurements is either tricky, requires workarounds, or not possible. So having a digital service monitor with P25 Phase 2 TDMA capability is very important. Frequency error is one of those. You must be able to determine the frequency error based on you don't have a CW signal, you've got a modulated signal, so you have to be able to measure and average the frequency error across multiple symbols and do statistical analysis. Again, RF power, we talked about, excuse me, HDQ PSK not being constant power. So again, how do you measure that without getting AM modulation errors? And it's TDMA. So how do you measure power when there's no signal half the time? Again, this is the importance of having a digital service monitor that can handle the TDMA signals. Modulation fidelity, an excellent measure of how good, what the quality of the signal is. And we're going to talk about bit error rate in a bit, but again, I'll just put a plug back in. Think of modulation fidelity as your speedometer, I guess I'll put it that way. Speedometer, you get readings between 0 and highway speed all along, so you can measure quality linearly across different levels of signal, from full strong signals all the way down to weak signals. When we're talking bit error rate, we're talking about at the very extremes of our coverage, and we're talking about after forward error correction has already failed, we start to get bit errors. So there's a lot of things that have the quality of the signal has degraded significantly by the time you start getting bit errors. So that's why I always like to point out the modulation fidelity. It's kind of often overlooked when you're doing P25 work. Moving right along. Receiver sensitivity, obviously this is where in an analog system you use a SINAD test, and of course the radios in these base stations are analog radios, and you can do SINAD tests on them with this service equipment, but in order to test them in digital mode, you have to be able to generate test patterns and compare test patterns and calculate bit error rates. Just skipping right along. Symbol rate error. So this is a measure of clock jitter is the best way to put it. So you're measuring how well the clock, let me back up just a second. In a system like this where everything at TDMA, where things are happening in 30 millisecond slots, it should be obvious to most everybody that everything has to be well synchronized. If you're not synchronized, you're going to transmit, you're going to bleed over into another slot. And so clock becomes very important. Synchronization and clock becomes very important. And there needs to be a way to measure how accurate that clock is. And that measurement is called symbol rate error. And it's a little bit confusing because the specification is in millihertz. It's a lowercase m. Some people think it's just megahertz where somebody misspelled or didn't uppercase the m, but that's millihertz. So in fractions of a hertz, how close we are, and obviously the closer to zero, the better. And the spec for phase 2 is approximately 60 millihertz. You'll see that when we go to do our actual demo. Okay, in order to be able to test phase 2 infrastructure radios, you need the R8000 P25 phase 2 option, which is available for all of our R8000 series service monitors that you see here. The R8000 A, B, and C models, the 8100, the 8200, and the R8600 radio test hub. If you're not familiar with one of these and you're interested to find out more, let us know, and there'll be a link to our channel partners and manufacturers reps at the end of the video. So when you have that option, how do you hook up to the base station to do this test? So this is what really the only connections that you need. You need to be able to, first of all, the base stations need to have an external reference. Typically your base stations are synced to a GPS source. And so in this case, the R8000 series service monitor has a 10 megahertz external reference. You feed that in, and now the two instruments are locked together so that error measurements aren't caused by the fact that the clocks of the two devices are different. In a lot of cases, these base stations won't run without an external reference, which is the case of the one I'm using today. Then you need to be able to generate a signal into the receiver. In this case, I'm going to use the RF gen out port on our service monitor, and then you need to be able to take the signal transmitted by the base station and feed it in to the service monitor. I'll be going into the RF in and out port, which is capable of taking up to 150 watts. And most of the time when you're doing these tests, you're not running at 150 watts, but it's good to know that the instrument can handle the multi-watts that's being transmitted in test mode. And just a reminder here that this ability to take your base station and feed it directly into your service monitor, in my mind, is what makes a service monitor a service monitor. If your piece of test equipment would be damaged by transmitting directly into it, then you've got a nice piece of RF test equipment, but you don't have a service monitor. And so that's just my definition of service monitor is the fact that you can take it out to the field and hook it up directly without having to put a large attenuator on there. So that's just a little plug for what a service monitor is. I'm connected, in my case, through Ethernet to the laptop running the manufacturer's software for controlling the base station. And I'm going to try to keep this presentation as manufacturer agnostic as possible. So I won't be telling you what kind of equipment I have or showing you any of their software, but it works pretty much the same for every manufacturer, every OEM. Okay, so what I'd like to do now, and I have this equipment set up out in the hallway because of the fan on the base station can be quite loud, especially when you're transmitting. So I am using what we call the remote front panel to control my test instrument. It's actually sitting on top of the base station out in the hallway. And so you won't have to put up with the fan noise. And I'm controlling it remotely. I can actually, with a touchscreen, can actually operate the instrument by touch, but I'm going to use my mouse so that you can see where I'm actually touching. Again, this instrument is hooked up to the base station. As I talked about earlier, the RF in and out port is receiving the power from the transmitter. The RF gen out port is generating signals into the receiver, and then my 10 megahertz reference is going to the 10 megahertz input on the base station. If you're not familiar with our service monitors, it works a lot like the old R2600 series, if you're familiar with those, but let me just give you a 2-minute rundown. Everything on the screen is organized into 4 different zones: an RF zone, a modulation zone, displays, and meters. In order to navigate between them and through the options, there are vertical soft keys, but at the top level, there's a real easy way to jump between the 4 zones, and that is to look at the shortcut keys. That's the white outline around the number keys. Now, the layout is different between the R8000 and the R8100 and later. So if you have an R8000, your pattern is a little different and your zones are laid out differently, but I'm gonna stick to this is the R8100 that I have. If I press the number 1 shortcut key, it goes to the RF zone. Then I have all of my settings available on the vertical soft keys. If I have more than will fit, there's a more 2 of 2, and I can switch back to more 1 of 2. Again, very quickly jump between each of the zones. I'm currently in analog, so my modulation zone is just my audio zone. Now, I have the instrument set up in absolute factory default. I didn't want to cheat and prepare the instrument to avoid having to navigate through, because I want to show you just how easy it is to learn and to use this equipment. It's designed around the way that you work and think, and it's designed, the design principle is we want to give you as much information as possible on the screen at one time without having to jump through hoops and menus and submenus and windows and sliding things around and everything. It's very easy to use. So let's do some very basic setup here. So first of all, my R8100 gen out port does not have the hardware-based extended gen out range. What that is that you can get your R8000 or 8100 or 8600 or 8200 with a gen out port that can go down to -125. By default, it's -90. In my case, I've got a 30 dB attenuator on my gen out port. Again, my unit hasn't, it's an old demo and it doesn't have that hardware in it. So I go into my settings, system settings, I come down to more, RF level offset on, come out to my gen out port, and I'm gonna come in here and tell it I've got a 30 dB attenuator on the gen out port, so I can generate down to -125. Okay. So now you can see that my okay, so I'm currently in monitor mode. That means I'm ready to receive signals. So let me control the base station. I'm gonna go over and I'm going to have the base station put out in this case, I'm going to do a P25 phase 1 signal. Now, I haven't changed the frequency yet. What frequency is it on? RF zone, monitor, 851.375. Okay, and you can see here I've got, and we know that it's FDMA because it's not, the power's there constantly. It's not jumping from 0 to full power. But I'm still in analog mode, so I need to go to P25 mode. I press the blue test button, test mode, project 25. 1, 2, 3, boom, I'm active. So those of you who have used some of the other service monitors out there will know that this is a process that can take a number of minutes on some of the other ones. Just wanted to put in a plug. Okay, so I am in P25 mode, and I am seeing this test signal. Let's go to my display zone. So the number 2, select display, eye diagram. So we're in phase 1, so this is a C4FM signal, and I've got my modulation fidelity, symbol deviation, symbol rate error. I'm receiving that P25 phase 1 signal. Okay, so now let me unkey the base station and let me switch it to a TDMA signal and power it back up. All right, so now and of course make sure I've got the right, I didn't switch it. There we go. All right. So now I'm transmitting again, but you can see it doesn't look right because I'm in phase 1. So test mode, P25 phase 2. And let's go back to our spec and view. And let's double check I've got the signal. Okay, and I told the base station to transmit 851.375. You can see that going on there. Of course, the base station is transmitting in both slots, so you're seeing constant power level there. There's my power level measurement. And, oh, okay. This is why it's important to understand the two different modulation schemes. Right now, the base station is outputting a signal that's HDQPSK. My service monitor is expecting HCPM, so I don't actually get, I'm not synchronized and I'm not demodulating properly. So if I go to my P25 phase 2 zone and change the type to HDQPSK, you'll immediately see that we start to get updates on mod fidelity, symbol rate, symbol deviation, and symbol error rate. We can also switch over in our display to the eye diagram. And there you have see the long dwell time. Okay, now one of the things you're seeing here, just a quick tip, you're seeing these numbers jumping around quite a bit. So we have in our system settings, so settings, system settings, the ability to turn on some measurement averaging. So for our digital measurements, I'm going to turn that on, and I'm going to tell it to average 20 readings together. I'm gonna go escape back to the main screen. And now you can see I've got consistent readings. I've got a modulation fidelity right around 1%. The P25 specs say that's got to be below 3%. Symbol deviation and symbol rate error. You can see here that I'm down around 0.1 or less millihertz. I can also turn on, if I go back to my P25 phase 2 zone, turn on my bit error rate test and have it compare the 1031 hertz tone to what's being transmitted, which is what's being transmitted, so we get 0% bit error. Okay, so I'm testing, I'm looking at the output. I go back to my RF zone and change the input units to watts. We've added a number of other settings recently. Okay, I'm putting out approximately 8 watts, which is the base station is in test mode, and that's its power in test mode. So there's your HDQPSK signal, and I am verifying that my modulation fidelity is good, my symbol deviation, my symbol rate error, my bit error rate on the transmit side. Not that meaningful unless there was the wrong test pattern or some kind of pretty serious firmware issue. Mostly we look at receive bit error, not transmit bit error. Okay, let's see my deviation, my frequency error. So you can see here I'm right on frequency. Of course, we're locked together, so that makes a lot of sense. Okay, so now let me toggle off my base station. Now we're going to go check bit error rate, RSSI, make sure I've got the correct. So when you want to do a sensitivity test of a phase 2 base station, there's an additional kink that you don't have to worry about in phase 1. That is that in order to send a test pattern into the base station, my service monitor has to be synchronized with the base station. And in order to do that, it has to look at the signal that's being generated by the base station, find the appropriate slot timing, and then transmit that test pattern. And then we can look at the sensitivity of the receiver. So this is an additional little thing you have to be aware of when you're testing TDMA base stations, in this case specifically phase 2. So what I'm going to do is I'm going to go into duplex mode, because in order to transmit a test pattern, I have to be receiving the base station signal to synchronize to it. So rather than just switching into generate mode, I have to go into duplex mode. I have to also be transmitting on the, so change my generate port, I have to be sending a signal out on the gen out port that's going to go into the base station's receiver. Right now I'm at -50, and that's fine. I go to the P25 phase 2 zone, and I have to actually turn on my modulation. Now I'm going to go over to my software tool, and I'm going to start the base station up. All right, and now you can see down at the bottom in the status, it says synchronizing to radio. And so it is, first of all, the first step is it's aligning the instrument's transmit and receive signal chains, and then it is picking up the timing from the base station and synchronizing to it, and then it can put out a signal. So now it's transmitting HCPM into the base station, and we're monitoring the HDQ-PSK output. Now I'm at 50 dBm. And I want to find out how sensitive the base station is. So I'm going to go to the RF zone.
You need to set your gen frequency.
Oh, thank you. Thank you, Wayne. Wayne, our CTO, always looking out. He's my guardian angel. Appreciate it. Monitor frequency. Nope, that's not the one. We want our generate frequency. Yeah, we want to be transmitting on the correct frequency. 806.0125. There we go. All right. Okay, and let me go back to the display, change that back to the spec in. And I'm going to show you real quick. I'm going to go into monitor mode and then come back into duplex mode and show you that synchronization process. So here we go into duplex mode. Just watch the spec in. It says it's synchronizing. You'll see it go off frequency. That's where the instruments transmit receive signal chains are synchronizing to themselves. And then it goes back over to the base station, changes the frequency, and it synchronizes with it. Okay, so now, thank you, Wayne. Now that we're transmitting on the right frequency, we now have our all of our measurements. Now, in the window for the control software for the base station, I am reading 0% bit error currently. I'm putting out -50. So let's find out how sensitive my receiver is. I'm going to go down to -110. And in my software, it's telling me now I've got, well, at minus, its RSSI is reading -111. There's some cable loss. I've got about 3 foot of cable, but it's still reading pretty much 0 bit error rate. So now I'm going to go in and lower that down to -116. From experience, the space station's sensitivity is about -117. So, oops, sorry guys, switching back between different windows. Okay, and so now I'm reading right around 4% bit error rate at -116. And so then I can decrease this down, -116.9. And look at my bit error rate again, and I'm right around 5%. So that would be at 5%. That would be my sensitivity of my receiver. Right there. And again, this whole process depends on being able to synchronize with the output of the base station. Now my instrument is transmitting on slot 0, but we do have the ability to choose, and that's the logical channel number. So 0. If I change this to 1, and have it resynchronize with the base station radio. Now in my software, I can see that I am measuring a bit error rate for the logical channels 1 instead of 0. Okay, checking time, coming up on about time for Q&A. So let me go ahead and come back to my presentation. Okay, so basically our 8000 series service monitors, regardless of which model you have or are interested in to meet your needs, all can do this. And they provide a full suite, full ability to install, verify the installation of not only the base station radio equipment, but also your filters, your cables, your antennas, and to do it all within the industry standards. And we put out the test patterns that are defined by the test documents. A couple things before we go into a Q&A. I wanted to kind of give you a high-level overview of the solutions that we provide. I keep mentioning the R8000 series service monitor. So the R8000 is a platform that we've released a number of products within for different purposes. The R8000C is primarily a shop or a bench. Obviously, it can go out in the field, but it was primarily designed to be on the bench. It has to have an external battery if you want to take it out, or has to be plugged into a vehicle. The 8100 brought along the internal quickly field replaceable lithium-ion battery to take it out into the field. The R8600 is the radio test hub that's primarily intended to be rack mounted or put on a workbench. It has the ability to take 150 watts, 100% duty cycles, 24/7, primarily intended for manufacturing or factory test environments. And then of course the R8200, which we just released, that has the built-in single port VNA. But on top of that, you have all of the firmware and all the digital protocols that you can load onto any of those instruments. You're talking phase 1, phase 2, DMR, NXDN, DPMR, Tetra, and so forth. We also have an application called AutoTune, which allows you to test your subscriber radios in a fully automated way. You plug in the radio's programming cable or test cable into the USB port on the instrument and hook up all your connections, and it will automate the process. There's a whole video on that if you're interested. Avionics RAM test. This is something we've added this past year. So if you've got customers or you have aeronautical portion of your organization, look into our ramp test. Positive train control. Again, these are side markets, but that some of you may be interested in. Again, free firmware upgrades. As long as you own the instrument, the firmware is free of charge. We put out firmware 4 to 6 times a year, and every time your instrument just keeps getting better. And then if you need an option that you didn't purchase up front, they're all field installable. We send you a 16-digit hex code that allows you to unlock features. And of course, we continue to add improvements and new features. And I mentioned here the ability to sweep cables and record cable sweeps for use in accounting for cable loss. There's also 3 software tools that are available, and I specifically want to mention the last one. So of course we have if you are integrating a test solution and want to include our instrument, there is an API programming interface. And I've shown you the remote software that I've been using to control the instrument. So this base station and instrument, even though they were just outside of this conference room I'm in, they could have been on the other side of the world connected to the internet, and I'd be able to operate it remotely. Finally, this point and click test script creation. So on my next slide, we have a great video on this, but I wanted to quickly show you. This is a tool that runs on a PC that connects through the Ethernet to the instrument, and you can basically, if you can perform a test manually, you can automate it by creating point and click scripts. This would be especially helpful for you if you're doing phase 2 site verification rather than having to constantly have to go through and push all the buttons like I was doing and having to switch back and forth between frequencies and settings. You could actually create a test script that would make those changes for you. And again, it's just simple point and click, create your scripts and run them. There's even a demo version on the website that you can play with without connecting to the unit. Or the demo can even allow you to connect to a unit if you have one and perform individual steps to send the commands. You just can't run or execute the full script. So if you're interested, let us know or try it out. And coming up on the end here. Again, I mentioned auto tune in a previous slide, but if you are responsible for, or there's someone in your organization responsible for testing and aligning the subscriber gear, we have an automated solution for that, so look into that. All right, this is my resource slide. This has my email address up there, our general email address, and a number of pages on our website that you may be interested in going to look for application notes, data sheets, for user manuals, for videos, for product information. If you'd like to contact in the US our manufacturers representatives, there's a great little tool there. You point and click on a map and it tells you who to contact. If you're an international person, then there's also a way to contact your distributor in your region of the world. And so I'm going to go ahead and look over at our questions. And I know we're running up on our time limit. I am not limited. I know, but I want to be sensitive to your time. So I'm going to answer as many questions as I can. And if you want to stick around and ask more questions, you're more than willing to. And as I pull up these questions, let me pop this out to where, there it is. Okay. I want to thank everyone for spending this time with me. I hope this was helpful. I sometimes get on a roll and move pretty fast, but my goal was to make sure that we provided something for everyone. And I want to thank you for following me through this series. If you just joined us again, I'll be putting out an email with a landing page for all of the content next week. So let's take a look at a couple of questions here. I've got yeah, so the question is, with phase 2 TDMA being more dependent on time synchronization and frequency shift, is it more important to align radios more often? It is, I will say this, if you've got really old radios that tend to drift a lot, obviously you're going to, you could run into problems sooner. So I think it's important. It depends on what you do. Do you typically wait until somebody reports a problem, or do you have a standardized PM cycle that you put the radios through? The systems are fairly fault tolerant, but and especially on the frequency side of things. And so, yeah, unless you've got a really old radio or a faulty crystal or something, you know, you definitely, if you're going from phase 1 to phase 2, obviously you need to make sure your radios are in tip-top condition and aligned as best they can be. Do you have to do it more often? I guess that would depend on what your experience is. Okay.
Well,
Another question.
can I say something on that, Chuck?
Yeah, go ahead.
In the obviously you want to be following the manufacturer of the radio's, you know, recommendations. I just find it interesting that recently one of the major manufacturers decreased their recommendation time on their phase 2 radios. So it is probably important to keep that in mind, that that if you're not checking them at least once a year, you're probably waiting too long. So
Yeah. Yeah, and Ryan is the one who put that question, and he just updated. He said they test in line every 2 to 3 years. And again, Wayne's correct that the official answer is you should always follow the manufacturer's recommendations. I know in practice, not everyone has the bandwidth to do it as often as sometimes the radio manufacturers recommend.
yeah,
But
but I did think it's interesting that a major manufacturer,
yeah,
decreased
decrease.
time recently.
And that's
Uh,
that's been my experience, is that you have to be reasonable, and the systems are fairly tolerant.
Also, speaking of time, the earlier when you showed your chart and you were showing the running your base station off of the 10 megahertz clock,
Hmm.
I mean, that was what you were effectively doing, sitting there on the floor, in the hall out
Hmm.
there. But normally, if the user is testing their base station um, in its site location, the base station itself will normally be connected, like you said, to an external reference.
Right.
And so ideally what you would do is you wouldn't be running off of our 10 megahertz clock. You'd have the base station run off its external 10 megahertz, and you would also connect that external 10 megahertz to the
To the instrument.
8000.
Yeah.
And so they're both
Exactly.
running off of the same source,
Right.
and now you perform your testing rather than
Yeah.
having the base station run directly
Ex-
off the 10 megahertz. So you only do that if that's all you have. But if
Right.
you have
Right.
a
Yeah. That's
hyper an external
very,
source,
very
it
true.
be for
Very
both
true.
units.
And the for those of you who have an R8000 series instrument, the 10 megahertz port is an input output port. It's not automatic though. If you want to put an external reference in there, you'll need to go in system settings and change the clock mode from output to input. I will say when you do that, it's always a good idea to make sure you have the external reference in there first before you switch it. Otherwise, things can get a little unstable if you run the unit without a clock. I've got another question. Somebody said, could I direct them to the computer control program for the RD100? So there's a couple different things I mentioned. I think I know which one you're talking about, but we've got the remote front panel, which what I was showing the instrument being remotely controlled. And then we've got what we call our process automation toolkit, which is the script building tool. Both of them are on the upgrades page. So if you go to freedomcte.com/upgrades, right at the very top, below that, you'll see there's all the firmware to upgrade your instruments. But right at the top, there's a link to the two software applications, Remote Front Panel and Process Automation Toolkit. Both of those do require a software option. The Remote Front Panel does come standard with the R80-100 and R80-200. It is optional. No, I'm sorry. It's optional with R80-100. It was included as part of the R8000 Premier package. But if you're interested in that, you can contact our sales. I had one more question I wanted to look at, and then we'll cut everyone loose unless, and again, I'll stick around for other questions. This is not specifically related to, well, it is in phase 2. So one user comments that when he's transmitting into the instrument, and sometimes when he stops transmitting, it looks like he's still transmitting because the last information that was being shown, in this case, he's talking about the power profile, but this is also true of all the measurements, they stay, and it kind of looks like the system's still transmitting. And this is something that's by design. I understand when you first run into this, it can be a little disconcerting because, oh, I thought I was still transmitting. There's still a signal there. But what you'll notice is that it's actually frozen. So there's no longer any updates. Your noise floor no longer moves on the power profile, and your numbers no longer jitter. This allows you to actually turn things on, make measurements, and then when you turn it off, the measurements are still there. So if you need to document or whatever, you don't have to keep pumping the power into the instrument. Got a thumbs up from Terry. Thanks so much for joining us today. All right, we've reached our limit. I want to thank everyone for coming. Again, follow up with questions. Please take time to fill out the very quick survey to let us know how we can help you or what further topics you'd like. And again, I'm going to stick around for a little bit. So if you've still got questions, or I can even bring up the demo again if you want to look at something specific. Otherwise, thank you so much for joining us, and we'll see you in the next one. Thank you, Sean. Thank you, Matthew. It's always a pleasure to work with you guys and do these webinars. David, thank you. Don. Hey, if I missed anything that, you know, something that you do when you're doing infrastructure checkout or PMing or aligning, or just let me know. I know there's, you know, I tried to be as comprehensive as I could, but there's obviously some manufacturers require different tests than others. I know there's, you know, like carrier squelch is an adjustment I didn't talk about, but that's in the manuals. Big thank you to Rudolph and Francois, two Francois today, and Brian. Yeah, Brian, you're not alone. He says, I'm kind of new to this P25 stuff, trying to learn all I can. So yeah, check out, if you haven't already, check out our previous videos that we dwell a little bit more on the standards and the underlying technology. And don't be afraid to reach out. There's a lot of good resources out there. Reach out to your peers and see what oh, and thanks, Ken Danker. Good to have you on the webinar, Ken. Good customer of ours. I'll go ahead and put a plug out for the wonderful folks down at Harris County, Texas. They're going through really hard times down there right now, but things are getting better. But they've been so willing to work with us and help educate us and talk to us about their needs related to P25 Phase 2. They've got, as I mentioned in the previous webinar, they've got a huge system, the Texas wide area radio network with, you know, like 150,000 subscribers or more. And, you know, every minute you can save them is a lot at each site. Adds up really quickly. So I want to put a shout out to all of those guys. Okay. And I'll hang around as long as you like. Let's see. Just quickly looking through. Thanks, Mark. I will see you next time. Make sure and let me know what you'd like to hear about. I think I'm going to entitle the next one Advanced Topics and kind of leave it open. And for those of you who are still on here, you get, I'm going to do a sneak peek. We are working on some expert panel presentations. It's going to be probably, maybe 3 or 4 weeks before we do our first one. But if you've got things you'd like us to put before our expert panel, and we're not talking about just Freedom people, we're talking about industry, international, renowned people who will be joining us from around the globe to answer questions about LMR and, you know, current state and where we're headed and specific technologies. Thanks, John. See you next time, Vladimir. All right. Well, it looks like we're winding down. Good question. So is there a video on using the VNA in the 8200? Yes, there is. Dawn, if you will go, and I'm going to pull this up. Let's see here. If you go to our website, that link to the video library, and it's not a training video per se, but let's see here. But I do a demonstration, so you can pause it and play it back. Let me see, where am I? Oh. If you go to, it's actually the second one down from the top, the R8200. It's kind of a full overview of the 8200, but if you skip through it, you'll get to a live demo portion. And I did, excuse me, I did some sweeping of cables and antennas and such. That'll give you a good idea. And if you still have questions, just let me know. All right, let's see here. Okay, looks like people are jumping off. Okay, folks, I will go ahead and shut this down, and I will see you in the next one. Thank you, guys. You've been great. Take care.